Hello everyone, welcome to today's live broadcast, the utilisation of LC-MS in the development of solid phase extraction methods. I'm Alistair Matheson, Editor-in-Chief of LCGC Europe, and I'll be your moderator for today's event. We're delighted to bring you this educational web seminar presented by LCGC and sponsored by UCT. UCT is a premier manufacturer and supplier of sample prep materials, HPLC columns, manifolds and additional accessories. The company's wide range of highly reproducible SPE columns allow the chromatographer a consistent extraction technique, and their expertise in silane manufacturing allows great control of the chemical processes involved in producing high quality bonded phases. UCT believes their commitment to ensuring customer satisfaction is accomplished by delivering on their promise, top quality, reproducible solid phase extraction products and unmatched technical support. We have a few important announcements before we begin. This webcast is designed to be interactive, and we encourage you to ask questions during the event. You can submit questions by typing them in the Q&A box, which can be found by clicking on the right-hand side of your screen, and we'll try to answer as many questions as we can. You can enlarge the slide window by clicking on the small green icon in the upper right-hand corner of the slide window, or by hovering your mouse over the lower right-hand corner and dragging the window to the desired size. The slides will advance automatically during the event. If you have any technical problems viewing or hearing this presentation, please click on the question mark help widget in the dock again at the bottom of the presentation window. Please note the valuable resources provided by our sponsor at the left-hand side of your screen in the green resource box. I would now like to introduce you to our speaker. We are pleased to be joined today by Michael J. Coyer, Ph.D. and F-ABFT. Dr. Coyer received a BS in chemistry with a minor in philosophy from the University of Scranton in 1986. He further studied organometallic chemistry at the University of Oklahoma Norman for 2 years under Professor Jerry Zuckerman. In 1998, Dr. Coyer moved to New Jersey and completed his Ph.D. in 1991 in physical and inorganic chemistry under Professor Rolf Herber at Rutgers University in New Brunswick. Since 1992, Dr. Coyer has been involved in forensic and environmental toxicological analysis. From 1993 to 1999, he was the director of Sierra Analytical Laboratories, a forensic environmental testing laboratory. In 1999, he became Director of Toxicology at Clinical Laboratories, CLI, in Thorpe, Pennsylvania, which later became the Laboratory Corporation of America. At CLI, he was responsible for post-mortem analysis and law enforcement toxicological investigations for several countries. He later became the Technical Director for CLI and was responsible for all laboratory operations, which included full service, clinical, toxicological and pathology testing. In 2002, Dr. Coyer was certified by the Society of Forensic Toxicologists as a diplomate and has been recertified in 2014 as a Fellow in the Society of Forensic Toxicologists for an additional 5-year term. Dr. Coyer is currently the Laboratory Director at the Northern Tier Research in Dunmore, Pennsylvania. His current duties as Laboratory Director include post-mortem forensic analysis, urine drug testing, DUI and DUID analysis, and developmental research. The laboratory also performs forensic consulting services for the public and private sectors. His research interests are in sample preparations using solid phase extraction. And Michael, if you could get started, that would be great.
Thank you, Alistair. I appreciate that introduction, and thank you, everyone, who's on the line. Hopefully today I'll give you a little bit of insight. My experience is working in solid phase extraction and general laboratory analysis. I've worked this is the 10th year I've worked with UCT, and over the years we've been able to work together on different products and applications. What I'll do now is just tell you a little bit about what I am hoping to do here. Give me just a moment to make sure that I'm good with my slide moving here, and okay. So what I'm going to try to do today is tell you some of the techniques and some of the things that I've learned in the 20 years of working in the lab, doing a lot of different types of sample preparation, not just in forensic, but also in environmental. So I have experience with environmental methods. I have a lot of experience in different types of matrix, but also what I've tried to do is make sure I understand the full operation. When we put together our standard operating procedures, it's a procedure of everything from chain of custody and sample collection to then finally putting out analysis. So it's a step-by-step process. And what I would like to sort of talk about is reverse engineering what we do every day in the laboratory. We start out by preparing samples and then analyzing them. But many times when you analyze a sample, there are certain caveats that you run into: instrumental, matrix effects, dilutions, limited sample volume. So all of these things come into play to finally getting an answer. I say this, that many times the extraction procedure is blamed for what went wrong. And many times that's not necessarily the issue, although it could be. So what we'll try to do is work backwards here and then talk about how I use LC-MS and pretty much MS analysis to optimize my methods, but also to troubleshoot. So hopefully I'll be able to pass some of my information and success stories along in such a way that everyone can walk away with a little bit more knowledge than they had before this call. So to start off, using LC-MS to optimize my SPE methods. When I think of an LC column, when we talk about cartridges and columns for solid phase extraction, that word is used interchangeably. But a lot of the phases and a lot of the science that goes into a solid phase extraction is very similar to that which is in liquid chromatography. So if we think of turning a cartridge or an SPE column on its side, it in a sense becomes sort of a liquid chromatographic column. In this case, though, we know that we use gradients when we use LC-MS, but usually we use a sort of start-stop chromatography where it starts out putting it on in an aqueous or buffered solution and then taking it off in 100% organic. So what I look at is try to look at the methods, but how do I diagnose the problems that come up in an analysis? And that's where using your instrument is important. When we talk about the phases of solid phase extraction, we usually have mixed mode. C18 are the most common. When I say mixed mode, those that have ion exchange as well as reverse phase. Can everyone see the screen? I don't. There we go. I apologize. My refresh seems to be slow, but when historically we're all used to what is reverse phase C18 chromatography. More recently, probably within the last 6 to 8 years, there's been a lot more phases that are being used, primarily PFP phases, biphenyl, phenyl phases for LC chromatography. These have application as well in the solid phase extraction field. And we've, at UCT, has looked at a vast number of these and really has honed in on some of the applications that are useful now, especially in the forensics and environmental market. So when we say C18 is a good starting point if you're working up a method, but don't forget about some of those other new applications and chromatographic columns. Now, when I get to looking at the slide, I have a slide here with the analytical structures and functional groups. The reason why I put this up is to get an idea of pretty much the general applications. When we think of reverse phase, we think of something that's nonpolar. There's not much charge associated with that. And the depiction there is a C18, a molecule, where it's reverse phase on the top. It sort of looks like a long piece of grass. And when you think of these being attached to either an LC column or a solid phase column, they sort of are these kelp beds that wag back and forth. In addition, we have to look at ion exchange, which is the electrostatic attraction when we have a molecule, and is depicted here in morphine. At a particular pH, you would have a charge. So you would choose your phase accordingly. Also, what we're going to be talking about is the solvents that are being used. Again, a common connection between solid phase extraction and LC is that acetonitrile and or methanol are usually organics that are used for washing columns and in sometimes eluting, but you also have buffers that are used to put a lot of these samples onto the columns. So again, the similarities in mobile phases: methanol, acetonitrile are organics, and water or some sort of buffer are part of your LC gradient. So again, this next slide will just be another a depiction of what the I apologize. I'm hoping you're seeing these. It's taking a few seconds for me to load, but I will just keep talking to make sure that I keep going through this talk. So in terms of now looking at some of the phases, again, here's an alkyl phase and a phenyl phase if we look at the structures there. So what I'd like to point out here, and what's important, is understanding that you have now an aromatic versus an aliphatic structure, and they do have different properties. The aromatic structures have a lot more electron density condensed into that phenyl ring. Now, what's important about that, and we think about a lot of our molecules, especially in the forensics, is a lot of those have phenyl rings. So we're able to then use those like attracts like sort of connections to have these attractive forces be useful, especially in liquid chromatography. So you start to see phenyl groups, fluorinated phenyl groups or biphenyl groups being used as LC in LC columns. So this aromaticity is important. And I will try to get across a little bit of why this is important in terms of using the LC columns and picking these and try to associate them with some of the solid phase extraction procedures. So again, the next slide is another diagram for looking at some of the different aliphatic and aromatic structures. Here you see biphenyl as well as your polyfluorinated phenyl columns. And notice there on the lower right-hand side where you'll see that there's hydrogen bonding. Some of the general chemistries that we use are important, maybe understanding what's going on in our extractions and our chromatography. So what I'd like to do then is to continue on and just make sure we stay with some of the general ideas. And let's not forget about aromaticity, aliphatic compounds, and what are these attractive forces? Why does C18 work better for some compounds where biphenyl might do better separation or PFP has some better separation? If we look at this chromatographically, we actually can look at the screen and see the retention times. And these retention times of the molecules are going to be associated with their attraction to the LC column, how they are chromatographed. Functional groups are something that we look at sometimes when I'm asked to understand a new molecule. Look at the molecular structure. See where there's electron density. Where will there be charge? Is there a carboxylic acid function? Is it an amide function? When I'm picking out my phase for my extraction, which phase am I going to use? Why will I use an ion exchanger? Or why will I use reverse phase? Or why will I use both of these, use a mixed mode? So understanding something as simple as the structures and the functional groups. With respect to what we see mostly in a lot of forensics are hydroxyls, carboxylic acids, and amines. So we're looking at the partial negative charges, partial positive charges, and then associating them with how are they going to be affected in our extraction? How are they going to be used in the solid phase extraction? And then after we collect these samples, how do they stick onto the columns? How do we see this chromatography? And which phase are we going to choose for our LC chromatography? Here's just a few molecules that you'll see. And what I tried to do is look at the ethanol ethyl glucuronide on the left-hand side, and you'll see that there's a large change in the pKa function. Without getting into it, these glucuronide moieties on this molecule make it much more water-soluble, make it much more polar. In forensic chemistry, parent drugs that are metabolized, like clonazepam and 7-aminoclonazepam, you get more polar compounds, just as you do with the marijuana, which is another molecule that you see something, you get drastic changes from the parents to the metabolites. Usually, if not always, they're more polar. So with respect to that, you need to understand that every group of drugs that might be, for example, benzodiazepines, which is a large group of parent drugs and metabolites, may not all extract and or chromatograph the same way. And I'll show you some slides in a moment. And here's just a few more slides that, again, looking at the various different structures, the different functional groups, functionalities, what would make a molecule polar, more charge, more oxygen functional groups would make something more polar. And we have to be cognizant of that when we're choosing our solvents. And again, if something is more polar, where is it going to chromatograph when we do our LC chromatography? How can we relate that back to the solid phase extraction? In the next slide, this is a slide that I put in here, and it's just something that I tell my group that when I work with them is when they say that we can't see a peak or we're not getting good recoveries or everything doesn't look very good onto the on the column or in our chromatograph or the data we're getting out of our mass spec, what are we putting on the column? Again, that word column. A column is a cartridge that we use solid phase extraction, but the column is the LC column, that which separates out the molecules to be read by the detector. And what this slide is essentially looking at how do we optimize that solid phase extraction? Well, we can follow the procedure, but how do we measure if it worked? And that's by using our GCMS or our LCMS. So in this case, the mass spec is giving us some indication of what was injected into that chromatograph. So if we're doing a dilution, if we're doing a dilute and shoot sort of preparation versus an actual solid phase extraction where you concentrate that, what this slide shows is that how much are we putting on the column? How much is getting injected and being read? And it's important to understand on column because when we're putting our samples onto our solid phase extraction, are we using enough sample? Are we using a half a mil, 1 mil? Are we using less? What do we want to get out of the end of this extraction? I've seen many times where just doubling your sample size from a half a mil to 1 mil does not change anything in the solid phase procedure. It doesn't change anything maybe in the column you're using, but it automatically gives you 2 times more of that analyte which you're putting on the column to extract. In addition to that, when we reconstitute a sample, how much do we reconstitute it back? If we're doing GCMS, we're usually only injecting 1 or 2 microliters. So at that point, taking it back up in 25 or 50 microliters, that again is a factor of 2. The last point I like to make here is that in your sample preparation or in your development of a method, how much are you injecting on the column? If you have the ability to inject more onto the column and your system is kept clean and your sample is prepared properly, just by injecting twice as much onto the column, 1 to 2 microliters, can give you twofold of a signal increase. So with that, I'm saying is that reconstituting your samples, doubling your sample size, and injecting twice as much, if all of those are just by a factor of 2, you could increase your sensitivity by almost up to a factor of 8. So it's important to think of on column. And not only is that on column for LC, this is also on column. What are we putting into our solid phase? Don't be afraid to use those samples because the solid phase cartridges and phases can hold a lot more than usually the amount of sample that's being put on. So again, this is just going through the similarities. Organics, methanol and acetonitrile, same mobile phases, used as a lot of washes in solid phase extractions. So what I want to talk to you now briefly about, very briefly, is your instrument, making sure you're optimizing your instrument. And below I have dwell times and cycle times. And this doesn't just apply to LCMS, this also applies to GCMS. Because when you're preparing these samples, you're making sure your instrument is optimized. If you don't have your instrument optimized to your particular group of analytes, you may not get a signal, and that could be, and sometimes is attributed to the solid phase extraction or the sample preparation, and that is not necessarily always the case. So what I'm going to do just very briefly now is tell you a few tricks that basically will help you to optimize some of your system. So in terms of looking at the dwell times, if we look, and this is just an application from my instrument where I've highlighted the dwell time. That's the amount of time that the instrument spends reading every point while it's making its mass spec applications. And if you look to the left in the grayed out area, that's a scan time. So how do we relate scan time and dwell time? Well, that's related to the number of analytes you're looking for. So essentially, when you're making a chromatographic peak, it's like small snapshots. It's taking a movie. So every so often, in this case, it's about 0.72 seconds. Every 0.728 minutes, or seconds, it's taking a picture. And what it's doing is it's taking a picture and it's calculating using a 50 millisecond dwell time. It's a function of how many analytes you're looking for. And below, that function will tell how many cycles can I get through so I can get data points. So what does that mean? Well, the more analytes I'm looking for and the longer the dwell time, the more time that scan has to go through its entire cycle so that it could look for all those compounds and try to get a reading as they're coming through. So if you have a longer dwell time, it has to sit on that point longer. What you're trying to do is you're trying to create the best scenario to get that peak, so then that peak will be able to be used more appropriately to make sure if the extraction is appropriate. So here, just quickly, you see if you double the dwell time, immediately the scan time then has to double, but your cycles go down. What that means is you cannot create as many points on your chromatographic peak. So with that, you want to try to optimize your scan times, which means the scan time is a function of the width of your peak. So if you have a very narrow peak that might be 0.1 minutes or just 6 seconds, and if you had a scan time of 1 second, theoretically you can get 6 points. Well, in chromatography, most people look to try to get 8 to 12 points, maybe up to 8 to 15 points, to try to get the best peak as possible. But this, again, is a function of the width of those peaks. So if you have a wide chromatographic peak, because it's not chromatographing properly on the column you've chosen, you may try to tighten that up by changing your scan time. Here's something that has a long scan time, and if you see here, there's 6 peak taken. And if you notice where all of the points of the scan are, you start to see this sort of follow the numbers. It sort of looks more jagged when you're looking. You don't have enough points, so you might have a scan time that's too long. By shortening that scan time, you may be able to then get more points on that particular curve. Why I'm putting so much emphasis on this is because a good chromatographic peak, good chromatography, will give you a better indication of how your extraction might be working. So you can't always assume that if your instrument isn't optimized, you can't assume that there's a problem or you've created a problem with your solid phase extractions or any of your extractions. I've seen many times when people think that the application didn't work, and then they will actually blame the extraction. Here's another slide that shows a shorter scan time, and what you see here now is you see more and more points being generated on that curve. That in itself might give you a better shaped peak, but at the same time, if your scan time is too short, you might be giving up some sensitivity on the other side. So what you're looking at is 3 things. And just try to remember that your scan time is the time through the amount of ions that you're looking at, the amount of transitions you're looking at, and how it's going to put points on that particular peak. And all of us have seen peaks in the beginning of our profiles that are usually worse than they are at the end of the profile. I always say that in chromatography, it's that beginning. It's those compounds that you're trying to get initially are the most difficult. After the first minute or so, your gradient sort of smooths out, and then basically you'll get better peaks as the run goes on. Lastly, here, and again, I apologize. They seem to be taking a long time to load, so I'm getting my timing down. But if you see the best scan time, you're looking at about 8 to 15 peaks. Why is that a number that we use? It doesn't mean if you have less or if you have more, but what you'll do is you'll get a nice sharp peak. Up on the left-hand side, you see how it has sort of sharp edges, where on the right side it's nice and smooth, and the bottom it's nice and smooth and Gaussian. But you might have too short scan times. I usually start as a 1 second as a default. That's a nice way to look at your peak, and now you can look at your peak time from start to finish, and you can tell exactly what that scan time might be, and you'll be able to count how many points you have. In the next slide, you'll see where I've highlighted a peak here, and it may be difficult to see, but you can highlight a peak, and then any of the data profiles, any of the GC or LC programs can usually generate each retention time and the intensity at those points. When you take those, you can actually make your own plot in Excel. And what that is get those data points, and by copying those into a text file in Excel, you can then put them into a scatter plot. Very simple. And what this gives you now is a picture of your actual peak, and you can count how many points you've created. It's a very quick way of doing some method mass spec development to try to get those best peaks. And in this particular case, there's 12 peaks on this point. I wouldn't go ahead and be making many adjustments because I've got plenty. The peak shapes look good. But now I know my instrument is giving me appropriate data. I can go backwards, reverse engineer, and evaluate the rest of the process, including the sample prep. So essentially, what we're going to do now is just talk about how I use chromatography. And what we do is, again, looking at the phases, you have your biphenyls and you have your aliphatic phases. But more importantly is the polarity of our solvents. Essentially, in LCMS, water and methanol and acetonitrile are the choices of the solvents being used for any of our gradients. And if we look here very close, water being our most polar, and methanol and acetonitrile have a difference in polarity, but they also have some different characteristics, their dipole moments and some of their other characteristics. So, but why do we choose one versus another? If I was talking before about polarity of solvents, polarity of molecules and metabolites, this next slide is a slide of a group of benzodiazepines. And that benzodiazepine to the left coming out early is 7-aminoclonazepam, a very polar compound. This is done on a biphenyl on the top and a PFP column in acetonitrile. Notice how the group of benzodiazepines mostly stay together. Here's where, when you're looking at peaks, that you say, oh, if I'm looking at an entire group, they're all going to chromatograph or extract the same way. That's not necessarily the case. With 7-aminoclonazepam was a troublesome compound, and I'll show you a slide earlier how UCT made, after they realized this, made suggestions into changing some of the wash solvents, and then all of a sudden what was being washed off a column because the phase was too strong was actually washing some of the 7-aminoclonazepam and other polar compounds off. So by using that reverse phase biphenyl LC column, we realized that a polar compound like 7-aminoclonazepam doesn't stick. Well, if we look at this gradient, if it was coming off at about a minute, if we look at our gradient and look at about a minute on that time frame, that's at about 20% or so. So what that tells me is that if I have a strong wash solvent that's 20% acetonitrile or 20% methanol, am I washing any of those compounds off my phase? Am I washing them anywhere off my solid phase extraction cartridge? And how I can see that, how I can view that, is by looking at it, how does that compound chromatograph? using the LC-MS and understanding why does it come out early. If it's polar and it's coming out at 20% organic, is my organic wash too strong in my phase? And you can lower that organic wash just like you're lowering your gradient, and it could stick onto your column. So more and more groups of compounds are becoming parts of our extraction procedures, not only in forensics but also in environmental. So we're using these tools in the mass spec or the LC to try to help to understand what might be going right or what might be going wrong in those groups of compounds in our extraction. This is just an LC column of a C18. And now look at the difference in acetonitrile and methanol. This is the exact same gradient. This is just the difference of acetonitrile and methanol in our gradient mobile phase. And notice the peaks that are red and pink to the left. That's amphetamine and methamphetamine. And the green peak that's coming out between 0.5 and 1 minute is morphine. These are small polar compounds. To the right, we have nordiazepam, alpha-hydroxyalprazolam, and the brown at the end is diazepam. Here's some benzodiazepines. But what I'd like you to notice here is notice how some of the early eluders on the C18 come out earlier, and then some of the later eluders, when you're just changing the solvent in the methanol, come out later. So your solvent choice is very important, not only in your LC, but also in maybe your wash solvents and some of your solid phase extractions. Don't just choose one or the other. Look, and what's important now, and I think what's really interesting, is look at your wash. You couldn't look at your wash solvents before using primarily GCMS, but now you can take your wash solvents, dry them down. If there's water or any organic, you can actually run a very quick LC-MS spectra and see if something's being washed off your column, because it would be in your wash solvent. We do that routinely in some analysis when we're trying to do new development, because we want to make sure we've chosen the proper column or that we're not washing something off of our column because of the method. Now, this next slide is a depiction of using all of the different acetonitrile and water as our mobile phase. But above on the top, we have a C18 chromatograph, a phenyl LC column, a biphenyl column, and a PFP column. I apologize for some of the peak shapes, but I want to point out that this is all done in the same gradient with the same exact acquisition method. And all we did is we changed and we looked at how are these compounds reacting to the phases in the LC. How are they then, could they be related to how they're coming off in the solid phase extraction cartridges? So these aren't optimized because it's one gradient, but notice the difference in the C18 and the phenyl group. These are very reverse phase. There's not much ion exchange. There's not much electron aromaticity as there is in the biphenyl and the PFP. What I'm pointing out is here is, again, look at the pink and the red that are the amphetamine, the methamphetamine. Notice how from C18, just by changing that to a phenyl, how it loses some of its retention and it comes out very early. That means that this is a very polar compound and it's in a reverse phase liquid LC column. It's not going to stick. Polar compounds do not stick as well on nonpolar phases. Now you get down to the biphenyl and the PFP, which are both phenyl compounds. They're both phenyl compounds in the phases, and they have similar retentions. Remember, a lot of the molecules that we're dealing with in forensics and toxicology, as well as even environmental, if they have rings, then they're going to have that pi-pi interaction. And if they have a pi-pi interaction of the electrons to the biphenyl or the phenyl phases, you're going to get more retention. This next slide is just the exact same experiment we did prior, and it shows you the difference in just changing the methanol and from acetonitrile to methanol. Again, solvent, how strong is that solvent? How does it wash it off the column? How early does it elute it off that LC column? If the solvent is strong and the compounds are, if methanol is our polar solvent, it's used as our wash solvent, it may wash some of these polar compounds off. So be careful that you're not washing things off your column if your wash is too strong. And you can use your LC to measure that, because by looking at the retention times, you can categorize your compounds as being more polar or less polar. And here's an example of UCT where just by changing the wash solvent from 20% acetonitrile to 5% acetonitrile, that 7-aminoclinazepam comes back in and it's not washed off the column. And that really looks like, when we're looking at the gradient again of some of these, is that essentially when you look here at between, again, 0 and 2 minutes, that's about 20%. If we looked at the gradient at 5%, it's going to be you're going to lower that, and it's going to be much lower, and you're not going to wash that off. So, again, I would use your LC to more understand what compounds in a group might not be acting just like you would expect in that particular group, because the fact that they retain themselves different on an LC column may mean that they're going to retain themselves differently on your solid phase extraction phase. And here again is 7-aminoclinazepam. I use this because this is a dramatic example that I learned from, where just by changing the phase, you can see the difference in the retention. So understanding how it retains on a phase will give you some information as to how it might retain on an extraction procedure. So when we look at, again, the gradient and understanding how it retains, I refer back to the phase, the silica or the resin-based phase, or the silica phase that might be used in a solid phase extraction procedure. And here again is the same gradient, and you're looking where your phenyl group is the least retentive, and as you move down, you see the exact same gradient procedure, which is outlined above, is that just by changing that phase, that particular compound reacts differently. So essentially, using the pictures that I could generate from my LC chromatograms will give me some indication as to the efficiency of all of the compounds in my solid phase extraction procedure. So here again is one slide that someone had given me while we were putting this together, and it's important because when we're talking about two phases, polar and nonpolar is all there is. So essentially, if we use a helic column, which is more of a normal phase type, but it's a polar phase, helic is a silic. It also can be similar in a solid phase extraction cartridge, and we compare that to a nonpolar biphenyl phase. Notice that in looking at several of these opiates, their retention is reversed. And this is important to understand because now you look at something like on the top where it's the helic column, the 6-acetylmorphine being the most polar, sticks more to retains less to that column because it has less polarity. It's a polar phase in that LC. So if the phase is polar, compounds that are polar are going to stick more. So that's the complete opposite when you go and you take a polar compound and you try to try to put it on a nonpolar phase. Notice morphine in the bottom does not retain because it's the most polar of the group. Well, if it's on a nonpolar phase, then you would expect it to come out earlier. So solid phase extraction is something that was introduced and worked a long time with United Chemical Technologies, and a long time ago someone said they're going to teach me a lot of this, and absolutely, I've learned more about solid phase working with Mike Telepchik and UCT in the last 10 years than I ever thought I would. And I never thought that I'd be applying it then to some of the LC work that I do, but I use this to try to teach my group, but also to try to best understand, with all of the phases that UCT can supply, how do I understand how some of these troublesome compounds seem to give everyone difficulty, but when you try to start expanding groups into large groups of molecules, large groups of compounds, and doing one extraction, it doesn't necessarily always work. So really, what you have to do is you have to choose your phase and then look at optimizing your instrument, because you may have 40 compounds that you're trying to extract, and if a few of them have low recovery, that doesn't mean that you can't optimize your instrument for those compounds to still use that solid phase extraction. So what I found is that every compound doesn't extract 100% efficient on any particular column. But when you start enlarging your groups, benzodiazepines, steroids is a very large group of compounds that are vastly different amongst themselves. So to try to say, I want to extract all of my compounds out on one column, that might be difficult. You may be able to extract those compounds, but those that don't have the same efficiency can be increased by using better instrument parameters. Again, lastly, in getting to the end, is that when we're looking at solid phase extraction, we talk about reverse phase, we talk about ion exchange. The same terms are used when we're doing LC chromatography. Reverse phase columns, normal phase chromatography. If we have a gradient in LC, it's because we're starting at a lower organic. We might be starting at 5 or 10% to put our compounds onto that LC column to then take them off slowly as we move that gradient. Well, when we do solid phase extraction, we're putting our compounds onto our phase using 100% buffer, 100% aqueous. We do our washes, which are sort of gradient washes, and then we take them all off using a strong organic. Well, that is essentially why it's been termed the start-stop chromatography. You put it on all at once, you take it off all at once. But in liquid chromatography, we put everything on, and then we slowly change that gradient. And I think that's where understanding your wash solvents and polarity and the different solvents that you choose, not only for your extraction, but also for your mobile phase, are important. And essentially, in summary, what I tried to do is I tried to, again, reverse engineer, understand and making sure my instrument parameters, the solvents that I've chosen for my gradients are the best solvents. When is methanol more appropriate than acetonitrile? Sometimes with acetonitrile, it's still been thought when it was expensive that I just want to use methanol. In some cases, in my opinion, and what I've seen, is that acetonitrile seems to be more forgiving when you're doing LC chromatography. So try those different solvents, and then take that same knowledge and use that in trying to best clean up your samples, create the best washes, because everything can stick onto a column, but depending on the adsorption, depending on the attraction of that solid phase to those particular molecules, your washes are very important into understanding what did I wash off. Did I wash off the matrix, the unwanted matrix, or did I wash off my compounds of interest? And remember, it's not wrong to take a look at those washes and see what's in them using your LCMS. So finally, in closing, is that I tried to use the same properties of solid phase extraction and liquid chromatography, the phases. The chemistry is the same. How do I use those applications to help develop and understand where my solid phase extraction can be enhanced or where I may be running into problems? The LC can be used as a visual aid. What I mean by that is, if something is being put onto a reverse phase LC column and it comes off early, you can assume that that's more polar. That's a more polar compound, because a polar compound with charge is not going to stick onto a non-polar or reverse phase column. So if we know that, then by applying even the same properties as I showed back with helic columns, if you have a polar column and a polar compound, it's going to stick very, very much, and it's going to retain stronger. So these same properties are properties that we would use in understanding the solid phase extraction. Optimizing your instrument at any time becomes the most important part of your entire analytical process. too many times a cartridge, a column, or a sample preparation procedure is blamed for a bad peak. It's blamed for recoveries, and it's not always necessarily the case. So what I like to do is work out my solutions in any process from the back forward, going from my mass spec back when I can, and trying to understand where I may have run into some issues. And is it the method entirely? Is it the sample prep? Is it how much I'm reconstituting? Or even is it the reconstitution solvent? I see a lot of people sometimes use 50-50 mobile phase to reconstitute. Some people use a lot more organic. And what you have to remember is that when you're dealing with the gradient, the front end of your LC is usually the most difficult to get the best peak shape. And usually starting out at a reconstitution solvent very similar to your initial gradient helps to sharpen those peaks up. So again, working through the solutions and understanding what this all means in terms of the entire procedure. And then lastly, I like to use my LC and then my previous knowledge and experience and the vast number of different types of phases that UCT has available to try to then optimize specifically for some of the applications. Right now with the new compounds, especially synthetic cannabinoids, are a challenge. Steroids have always been a challenge. Even more so, benzodiazepines are difficult. So when you get into larger groups of classes of compounds, use not only your LC, but use your extraction method, and then look at it as an entire process and not just necessarily a sample prep, because your chromatograph, your mass spec, all of that data acquisition is what really tells you what's going on in your sample preparation. So with that, I think I'm at the end of my talk. I appreciate everyone's patience, and I thank you for the opportunity to talk to you, and hopefully I've passed along some information that could be useful in some of your applications.
Thank you very much, Michael. That was a fantastic presentation, so thank you very much. And before we get started on the question and answer session, I would like to remind our audience how to submit questions. You can submit questions by typing them in the Q&A box located on the right-hand side of your screen, or by clicking on the red Q&A widget at the bottom of your screen. We'll try to answer as many questions as we can. And our first question, Michael, is what do you find more critical for the optimized LC method? Baseline resolution for all compounds or quick overall run times?
Well, it depends. I think what you have now with mass spec, and depending on what type you have, when you choose your transitions, and you'll have a quant ion and then you'll have a qualifier ion. If those transitions are different enough, then chromatography, I don't want to say becomes less important, but if that transition is different, the instrument itself and your parameters that you set up in your acquisition, which again are your dwell times or your scan times, can actually still give you very good peaks. I think baseline resolution is always what we're shooting for, and it was much more necessary when it was just LC and UV spectra. But when we're looking at now transitions that are specific, I think what we try to do is we try to optimize our instrument parameters. And that's because everyone is trying to get more screening done on LCMS, so they want more compounds done. So your choice, and what's critical in my opinion, and if this is on the same subject, is you've got to extract and prepare a sample. To me, what I've seen is when you dilute a sample and you put it on the instrument, you're having difficulty getting not only the peaks, but you're going to have difficulty getting good chromatography because of matrix problems, because of just sample problems. So it doesn't take long to do a good solid phase extraction. And it's in UCT has products that are a couple of steps. Once you do that, going back to that slide where what are you putting on column? Are you putting enough on column? And if you are, you're going to get a signal. And if you're going to get a signal, what is that instrument parameter set up? Your chromatography is a function of time. So if you want it fast, you're going to give up chromatography.
Okay, thank you very much, Michael. And someone wants to know, do you recommend the addition of buffers into LC mobile phase systems?
No. And here's why. Because once you start introducing buffers like phosphate buffers, what you're going to do is, remember at the Q0 of your mass spec, it's very hot. You're getting rid of all that solvent. You don't want to be putting phosphates on the front end. You'll get dramatic suppression of your signal. Plus, you're going to put salts on the head of the front of your instrument that you don't necessarily need. In most cases, a formic acid is plenty. Some people might use some different sorts of acids, but I don't, and as practice, wouldn't use and wouldn't recommend any buffers. Buffers are for the extraction, not necessarily for the analysis.
Okay, thank you. And someone else wants to know, how can we avoid interaction with polymers?
A lot of praying helps. I don't have much experience with polymers, but what you, again, I'm not sure exactly what the application would be if it's polymers, but if these are polymeric compounds, they should be able to be washed out. And that would be, if it's a sample prep, depending on your choice of a cartridge or a phase or a column, might help you to wash those out. So understanding, again, what those polymers are and the solubilities, you would either keep or get rid of them if you had to, using an appropriate solvent or wash solvent.
Okay, thank you. And someone else wants to know, does filtering a sample help with sample cleanup?
Absolutely, because with respect to, again, a product that UCT had, it's the FAST, which is a filter and shoot. It's designed essentially to do two things: to take out small fine particles that are going to clog your LC columns if you have a 3-micron phase or even a 5-micron phase, and it also has a phase that cleans up the matrix. To answer the question on filtering, the filtering is to save your instrument, and especially your columns, because you have very small particle size in those LC columns. So if some people don't filter them, they may do a ultra-high centrifuge. You want to get those particulates out. In terms of the instrument, again, optimizing your instrument, if your instrument is clogged, if your needle is clogged, or your column pressures are going up because it's being clogged on the front end, and you're not using a guard column, you're going to kill your instrument. And really, a filter is not something that takes very long, but it saves you a lot of instrument issues.
Okay, thank you again, Michael. And the next question is, with the rapid and ever-growing diversity of designer drugs, do you find that this has put added pressure on the development of new assays, or, since they are still chemical analogues of existing illicit drugs, existing methodologies can be tweaked?
I think that's a great question. You know, reinventing the wheel is not something you want to do, but it's something you can still consider. What I mean by that, and I think the best example is synthetic cannabinoids. We started initially doing screening for synthetic cannabinoids, and now it's about the 5th generation of compounds that are out there. So they all have similar structures, but as the 3rd and 4th and 5th generation have come up, they look much different. So what I recommend is what you may have in some of these groups of compounds, as they grow, it's difficult to say that 40 or 50 compounds or even more in a group are all going to extract, chromatograph, or even respond to a mass spectrometer the same way. So what I like to do is categorically understand which ones I can extract out and overall get my efficiencies. If I have some compounds that extract very well, 70, 80, 90%, but I have others in that group that are only 20 or 30%, don't change your entire sample prep procedure, but you may have to tweak your instrument to get better response of those lower recoveries.
That's great. Thank you very much. And someone else wants to know, how can we remove high salt content in the sample?
Well, depending on what high salt is, that's difficult. Depending, again, if it's in solution, salting something out would be a function of some sort of, well, if it's solid phase extraction, you're going to try to pick a cartridge where those salts may stick to that. But in getting salt out of a solution, you have to use a nonpolar solvent and somehow do some sort of partitioning. So depending on the salt in particular, some salts, by adding certain other chemicals, will precipitate right out. I know if you have silver nitrite, for example, as a salt, and if you add chloride to that, you can get silver chloride to precipitate out. But in terms of that, that's sort of a multi-answer question. But usually, a partition between different solvents might be a good start.
Okay, thank you again. I'm just trying to catch the next question or see if there's any more. Someone wants to know, what is your experience with the helic chromatography in a high throughput setting in regards to doing long equilibration times and extensive organic solvent use?
Well, helic is, in a sense, the opposite of what we're used to doing in laboratories in reverse phase. I think helic has its applications for specific compounds. Glucuronides, I think, have a lot of application. Polar compounds, if you're looking to do some sort of separation, you're going to obviously have maybe longer run times. But with respect to the characteristics of the compounds, then you're going to be looking at your gradient times and the solvents that you choose. I would say that every lab has some sort of reverse phase, even if it's a C18 column in their lab. And by taking those, and the best way is to do the comparison. If helic for throughput isn't something that I've seen in other laboratories, throughput usually is based on reverse phase, but I look at a lot of forensic labs that use compounds that are more amenable to that sort of testing.
Okay, thank you very much. And a few other people have written to say that was a great presentation, Michael, so thanks very much. And unfortunately, we're out of time. I want to thank the audience for their interesting questions and participation in today's event. I would also like to thank our sponsor, UCT, for making today's educational webcast possible. Today's webcast will be available for on-demand viewing till September of next year. You'll receive an email from LCGC alerting you when this webcast will be available for replay. We invite you to send this email to any of your colleagues who may have missed today's live event, and we look forward to seeing you again here soon. Goodbye.